What if you can hand the model a dataset it has never seen before, no training, no fine-tuning, and it just predicted the future accurately? Today we are going to find out exactly why that works by building one ourselves. Hey everyone, I am Alexei, software engineer at Google, though everything I share in this video is my own opinion and not Google's. This is monthly tourism data across 366 destinations. This model has never seen it, it was never told what a holiday season is, and yet it achieves 7% error rate. This is the promise of a time series foundational model. Just like GPT, the patterns of language by reading the internet, TimesFM learned the patterns of time by training across energy grids, road traffic, financial markets. By the end, you will have written the patching, the attention, the normalization, the loss function from scratch, and you will have watched it learn. We start with the data. We are pulling from the Decode-only library, a package built specifically for probabilistic time series. Our dataset is a tourism monthly. It's 366 real destinations, each with monthly visitors, counts ranging from 67 to 309 data points. Over 100,000 data points in total. So the reason this dataset is perfect for us is that it has two properties that make forecasting genuinely hard. One is the scale variance. Some destinations get thousands of visitors and some get millions. So there is a strong seasonality, meaning the same spike happens every year like a clockwork. These are two things a model needs to learn to be useful in the real world. Before we build anything, we need to look at what we're actually dealing with. We pick three random series. Notice series 0 immediately. There is a massive spike every single year. That is almost certainly peak holiday season for that destination. The model has never been told this. It will have to figure out purely from the numbers. Now look at the scale difference between the three series. One sees around 20,000 visitors per month and another sees around 200,000 visitors per month. If you just threw this into the same model without any normalization, the large series would completely drown out the signal from the small one. That is the problem number one we will solve. Before we build a toy version, let's see the real thing in action. This is TimesFM, Google 200 million parameter foundational model for time series. We pull it directly from Hugging Face. No custom training, no fine-tuning. We literally just load it and hand it data. To run the inference, we need to do a one call. That's it. Notice what comes back. Not a single prediction line. TimesFM returns a point forecast and quantiles. Think of that point forecast as the model's best single guess for each of the next 24 months. The quantiles are its confidence intervals, 10 of them, from the 10th to the 99th percentile. This matters. A single line tells you where the model thinks things are going, but the quantiles tells you how confident it is. A tight fan means high confidence. A wide fan means the model is genuinely uncertain. That difference is worth more than the point forecast alone. Look at that. The red line is our point forecast. The shaded band are the 80s and 90 confidence intervals. The actual future data sits underneath. So we have 7% MAPE. The model nailed the magnitude and the timing on the tourism peaks and noticed how tight the bands are. They hug the actual data closely. This model isn't just guessing the right number, it knows it's right. That confidence is mathematically built into the architecture. This is what we are going to build. Let's get into it. To understand how TimesFM works under the hood, we need to talk about patching. TimesFM doesn't look at one number at a time. It divides long sequence into manageable chunks called patches. Like on this cell, we are taking a simple sequence of numbers and breaking it down into fixed length segments. We are reshaping our 64-point series into a grid of 8x8 patches. We'll use this approach in the upcoming cells. We can see the visualizations of the 64 points broken down into 8 patches. Each patch has a length of 8. Here we implement TimesFM style preprocessing before the transformer sees any token. The mask mean std, it finds the first patch with at least 3 non-padded values and computes the mean and standard deviation strictly from valid entries. The forward transform here, it normalizes all patches using the statistics from that single reference patch, then resets the padded positions back to a constant value of 0. What basically happens is that we inspect the padding array to locate the first patch that has at least mean valid non-padded entries, and once we extract the index of the first valid patch, we apply the padding mask to calculate the sum, mean, and standard deviation using exclusively the valid data. To understand what is happening, we run our forward transform. So we mask the whole first patch, so it cannot be used for statistics. So then we also mask the last two values in every patch. And then the algorithm therefore picks patch index 1 at the first valid reference patch. Let's have a look at the output. We have original patch's shape, which is 8x8 with the batch size of 1. Then the normalized patches have the same shape as expected. Our mu is 11.5 and the sigma is 1.7. So if we inspect the second patch, it starts from 9, 10, 11, 12, 13, and 14. And you can see that the last two values are 0 because they are padded and explicitly overwritten after normalization. So this mirrors the normalization and padding behavior in TimesFM input pipeline. Next, we convert each normalized patch into a learned embedding vector that transformer can process. For this, we have a residual block here. Before we discuss it, let's do some info work around it. We first concatenate the normalized patches with their padding mask. We hope here that the MLP would be able to learn and distinguish between the two. So during training, the weights attached to the mask learn to act as a mathematical shut-off valve to cancel out padded values so they do not corrupt the embedding of the real data within that incomplete patch. So basically what happens is that inside the residual block, the main branch passes the input through the hidden linear layer and the activation function, followed by an output linear layer to finalize the projection into embedding space. Simultaneously, because our feature dimensions are changing from 16 to 32, our skip connection uses a linear projection to match this new dimension. We then add the skip connection to the output of the main branch to achieve the final mathematical transformation for the block. Alright, before we pass our new embeddings into the attention layer, we need to normalize them. In this cell, we implement RMSNorm. We are setting up our normalization model. But you will notice that we aren't using the standard layer normalization, we are using RMSNorm. Why the switch? The standard LayerNorm actually does two things. It centers the data by subtracting the mean, and then it scales it. But researchers eventually realized that the centering step doesn't really add much value to the model performance, and calculating that mean across the vector just slows down computation. So the RMSNorm drops the centering entirely. It simply scales the vector by its root mean square. By skipping that one step, we get the exact same stability, but it executes significantly faster. So basically, RMSNorm looks at the 128 numbers that make up the specific embedding, squares them, calculates the mean, and takes the square root. That single resulting number is the RMS. It divides all 128 numbers in the embedding by that single RMS value, and finally it multiplies that normalized vector by the 128-dimensional learnable weight parameter. Let's look at the math. So we have our original 2D vectors of different magnitudes, 2, 4, 1, 1, 6, and 8, and then we run it through the RMSNorm layer. Let's see what we have on the plot. We have original vectors, and then we have the vectors after going through the RMSNorm. So the plot perfectly proves our logic. The RMSNorm layer scales the vectors to a consistent magnitude without changing their underlying direction, which perfectly prepares them for the attention layer. Now we need to inject positional information into our model. Instead of adding static embeddings at the very beginning, we're using a rope, which stands for Rotary Position Embedding. If you saw the last video, we used rope where I go through the rope and explain each and every method. I won't rehash all of that here, but the quick summary is that the rope rotates our query and key vectors in pairs, which allows the attention mechanism to naturally understand the relative distance between tokens rather than just their absolute position. Basically, the rotation fundamentally requires a 2D plane. If we have a number 5, we can move it left or right or strengthen it by multiplication, but we can't rotate it. To perform a rotation, you need an x and y axis, so we need a 2D coordinate space. So by grouping dimensions in pairs together, rope is artificially creating a 2D plane out of our 1D list of embedding numbers. Once you have a point on a plane, you can swing it around the origin using the standard high school trigonometry, sines and cosines. Look at the printed outputs. At position 0, there is a 0 rotation. At position 1, the first dimension pair has rotated 57 degrees, and in position 2, 114, and in position 4, 229. So the fast dimension handle local contacts, tokens right next to each other. But the slow dimensions handle long-range structure, patterns across the full sequence. Now to self-attention. This is the core of the model. But before we write the attention layer, we need to enforce one rule. The model cannot look at the future. This is the autoregressive model, so it predicts step by step. If it is allowed to see the future while predicting, it's just copying and not learning. We block this with the causal mask. So the causal mask here, it's a function builds a matrix where every position is filled with a very large negative number, and when these scores pass through the softmax function, those positions become exactly 0. This future is mathematically erased. Now to the attention layer itself. It is a standard multi-head attention with two modifications. The first one is we apply rope to query and key vectors before their dot product, so the distance is baked into every similarity score. Second, instead of dividing attention scores by the static square root of head dimension, as in the original transformer paper, we use per dim scaling here. So this instantiates a learnable parameter for every single dimension passed through a soft plus activation. The model learns how much to trust every dimension individually. In our test though, we have an input embedding size of 1, 8, 32. Basically we have a batch size of 1, 8 patches with 32 features. We get back the same shape. So the shapes are perfectly preserved. The attention mechanism enriches the embeddings without changing their structure. And the causal mask visualization here shows the staircase pattern clearly. Patch 0 can only see itself, and then patch 1 can see patches 0 and 1, and so on. The actual attention weights confirm the upper right triangle is completely back, 0 attention to any future token. Basically, it takes an embedding and projects it into 3 separate vectors. A query, what the token is looking for, a key, the token's identity, and a value, the actual data payload. To find out how relevant tokens are to each other, it calculates the dot product between a token query and every token's key to get a raw similarity score. Next, it passes those scores through a softmax function, which turns them into percentages that add up to exactly 100%. Finally, it multiplies those percentages by the values. By splitting this across multiple heads, the model can look for different types of contacts, like grammar, emotion, and distance at the exact same time. Everything we built so far comes together in the decoder layer. This is the fundamental repeating block of the model. Let's look at how we initialize this layer. You can see it instantiates our custom self-attention here, and then it defines feed-forward up and feed-forward down projections. We also have a pre and post normalization for attention and a feed-forward blocks. So why normalize both before and after? So the time series data can have huge variance shifts. A single spike in an electricity dataset could throw the numerical scale of complexity. So wrapping both blocks with RMSNorm on each side keeps the numbers tightly controlled at every step. So our attention pipeline splits into multiple steps. First we run through the pre-normalization and then go through the self-attention layer. Then we have a post-normalization, and then if use residuals is available, we run it through the residual layer. And the same applies to the feed-forward block. We have a pre-normalization, we run it through the feed-forward up projection, then we go through the activation functions, then the feed-forward down projections, and then we have a post-normalizations. Let's look at our simple test. So in our output, we see that we have an input shape of 1, 8, 32, and then we have an attention weights of 1, 4, 8, and 8. So it's one batch, 4 heads, and 8 by 8 attention grid. The output is 1, 8, 32, which is perfectly preserved according to the input side. Basically, the decoder layer acts as a two-stage assembly line for refining the time series patches, using an ultra-stable sandwich normalization approach. In the first stage, attention, it normalizes the incoming data, lets each patch look back at previous patches to gather context, and using rope to understand exactly where it sits in the timeline, and then it normalizes the results again. It adds this newly discovered context directly to the original patch, the first residual connection. In a second stage, feed forward, it normalizes the data a third time, expands it to map out complex mathematical patterns, filters out negative numbers with the ReLU activation, shrinks it back to the original size, and applies the fourth final normalization. Just before finishing, it explicitly zeroes out any fake padding tokens so they don't corrupt the math, and adds this polished result back to the running stream, the second residual connection. Now we stack the layers and add the output heads. So the full stack decoder has three parts. The first one is the tokenizer. So a residual block that takes raw patches and masks, concatenates them, and projects them into embedding space. This is our entry ramp. The second is the stacked decoder layers. We have a module list of decoder layers stacked on top of each other. Each layer refines the temporal context, and then we have our output projections. This is where the time series diverge from language models. We have two separate output projections. One is the output projection point, a single number per future time step. And then we also have the output project quantiles. This is 10 numbers per future time step, the probability spread. Why both? A single best guess line is often useless without knowing how confident it is. The quantile heads outputs the 10th through 90th percentile simultaneously. You get not just the forecast, but the full uncertainty picture in one forward path. Basically, this is the masterclass that ties all components together. First, it takes your raw time series and their tracking masks and then glue them together. It pushes them through the tokenizer to convert them into rich, high-dimensional embeddings. Next, it applies a strict causal mask, a rule guaranteeing that patches can only look at the past, but never to the future. Then, it sends this embedding through a massive stack of decoder layers, with each layer deeply refining the temporal context. Finally, the fully processed data reaches the end of line and splits into two separate exit pipelines. One pipeline mathematically projects the exact future numbers, the point forecast, while the others projects a spread of possible scenarios, the quantiles, to show exactly how confident the model is in its projections. Let's verify our shapes. We pass in 4 patches of length 8. Look at the point forecast here. For each of the 4 patches, the model is spitting out a continuous prediction of 32 future steps. But the real magic is here, is the quantile forecast shape. It is 1, 4, 32, and 10. That is the one batch, 4 patches, 32 future steps, and exactly 10 distinct probability buckets for every single point in the future. We have built our entire model architecture. It takes a messy time series patches and spits out both a point forecast and a 10 quantile predictions. But here is the question: how do we actually teach it to be accurate? How do we punish the model when its confidence intervals are completely wrong? To do that, we use quantile loss, also known as a pinball loss. When you are predicting the future, being wrong isn't always symmetric. Think about it like this. If you are predicting inventory for a massive retail store, and you are trying to calculate the 90th percentile of expecting demand, under-predicting is the disaster because you run out of stock and lose millions in sales. But over-predicting by a few units is fine. Now look at the quantile loss function here. We calculate the deviation, the actual value, minus our prediction. And then we apply asymmetric weights. If you are targeting a high quantile like 0.9, the loss under gets multiplied by 0.9, a massive penalty, while the loss over gets multiplied by 0.y, a tiny penalty. The model is mathematically forced to push its prediction higher to avoid that massive under-prediction penalty. And in compute loss, we tie it all together into a single objective function that TimesFM can optimize. We calculate the standard mean squared error for our single point forecast. Then we loop through all 9 our target quantiles, calculate the pinball loss for each one, and sum them up. The model learns to draw the median line at the entire probabilistic fan of possibilities simultaneously. Look at the green line for the 0.9 quantile. If our error is positive, meaning we're under-predicting, here the line shoots up violently into the top right. But if we're over-predicting here, moving to the left, the line is incredibly shallow. The punishment is tiny. The blue line for 0.1 is the exact opposite. It heavily punishes overprediction. Now let's look at the right plot here. This is the crucial comparison. So the solid blue line here, it is the mean squared error. It's a parabola. MSE squares the error, meaning it punishes massive outlier exponentially. The dotted orange line here, quantile loss set to 0.5, which is the median. It forms a perfect symmetric V shape. This is a mathematical identical to mean absolute error. It punishes over and under prediction equally, but it scales linearly, meaning it is much more robust to crazy outlier data points than the MSE. By combining both of these loss functions, TimesFM gets the best of both worlds: the stability of probabilistic boundaries and the precise targeting of standard regression. In the real world, you don't feed perfectly formatted, pre-normalized tensors into the API. You feed it raw, messy CSV data. So our class is the master pipeline that handles exactly that. It takes raw time series data, cleans it, runs through the neural network, translates the matrix math back into the human readable forecasts. Right at the top, we initialize the default quantiles from 0.1 to 0.9, and then we also have a stack decoder as our engine. But the real magic of this wrapper is in the data pipeline. Now let's look at the padding function first, here, pad to patch multiple. Real-world data almost never perfectly divides into your patch lengths. If you have a patch length of 32, and you have 100 days of data, you have a reminder. Notice how we handle this. We'll calculate the needed padding, and then we pad the left side of the tensor. We push the padding into the oldest possible historical past. Why? Because the most recent data, the immediate present, is the most critical for the forecasting the future. We want that recent data perfectly aligned at the end of the sequence. We fill that distant past padding with a massive distinct float value, which the model immediately recognizes and masks out. Now let's go quickly through the three important methods: reverse transform, preprocess, and forward. They're all connected. In preprocess, we calculate the mean and variance of our raw input, normalize them so the neural network can digest them safely, and crucially, we save those statistics in last stats. Once the stack decoder here does its heavy lifting and spits out a prediction, it's still in that normalized space. The reverse transform function here takes those raw outputs, multiplies them by our saved variance, and adds back the mean. It maps the network abstract math directly back to our real-world data. Here, I run the end-to-end test to prove that our architecture works. We instantiate a macro version of the model, bringing our parameter count to about 87,000. We feed it raw 60-step tourism context data, and look at the forecast shape here, 116. We feed it our raw 60-step tourism context data, and out of that 60-step context, the model successfully returns a continuous 16-step point forecast into the future. And for our quantiles here, it returns a massive 1, 16, 10 tensor, 16 steps future, each with 10 distinct probability boundaries. Because it is time series foundational model, the goal of the paper is layer shot forecasting, meaning the model should be able to look at a dataset it has never seen before and predict it perfectly just by understanding the fundamental physics of time. To teach it that, we have trained it on a massive, chaotic mixture of entirely different industries. Look at the dataset we have here: electricity hour, traffic, M4 daily, and M4 weekly. We are pulling the dataset using the Gluon TS library. We have electricity hourly, which is the high-frequency energy consumption data with massive daily spikes. We have traffic, representing road occupancy, which has completely different weekly seasonal patterns. And we have M4 daily and M4 weekly, which is the macroeconomic and financial datasets. What we are forcing here is the neural network to find the universal mathematical patterns that connects cars, power grids, and money. And look at our final numbers. We have successfully combined over 5,000 distinct time series spanning 4 completely different industries, giving us a massive pre-training corpus of 25 million data points. In these cells, we are preparing for training. In the model config, we are defining the physical layout of the network. We set the input patch length to 32, This means our model looks at the past chunk of 32 time steps. We set our output patch length to 64, meaning the model will output its prediction in chunks of 64. Now let's do some crucial sanity check here. First, we have 4,000 valid training series. If we multiply it by 50, we get 200,000 total training series. Why we multiply it by 50 is because we randomly sample 50 times from those 4,000 series. And then if we divide by 64, our batch size, we get around 3,000 training batches. If we go to the start training cell, we know that we have 25 million data points. If we divide it by 32, we get 800,000 tokens. Then we divide the 800,000 tokens by how many parameters we have in our model, and it is 200,000. And the final number that we get is 3.8. So what we have is 3.8 tokens per parameter. Let me switch to the notebook in my Visual Studio where I already run the training loop. The model starts completely blind. At epoch 1, the loss is high. Then at epoch 10, 20 and 30, the validation loss is falling. It started to recognize patterns. The things that go up tend to come down. That seasons repeat. That context contains information about the future. By epoch 90, the training loss and validation loss are tracking each other closely. Large language models are trained with tens of tokens per parameters. We did it with just 3.8 per parameter, and it still learned. You see that the training loss is slowly declining, but the validation loss is actually fluctuating and does not change the parameters much. So this is the fact that the model is a bit overfitting. Now to the moment of truth. The blue line is what the model sees, 60 months of history. The dotted black line is what actually happened next. The dashed vertical line is where the history ends and forecasting begins. So TimesFM is red. It's confident, it has tight bands, it nails the direction almost immediately, it knows what comes next. Our model in green, it has wider bands, it's like being honest about what it doesn't know. But look at the shape, it goes up when the series goes up, and it turns when the series turns. It learned the seasonal rhythm of monthly tourism data from scratch. The metric table puts the number on it. We can clearly see that the TimesFM has an MAE of 195, but the our model has 615. There is a clear gap between our tiny model and the huge TimesFM model. Even though our model can capture the pattern, it couldn't capture the absolute values. This is why we have a huge difference between them. Okay, so what did we actually build today? 5 components. First, patching. It split the series into 32 time series windows. Each one becomes a token. Reference patch normalization. These score the whole series against the first valid patch. Forecast, then reverse it. The model never sees scales, only shape. A residual block tokenizer that projects each patch plus its padding mask into the model hidden dimension. Then 4 stack transformer layers, RMSNorm, causal self-attention with Rotary Position Embeddings, and 2 output heads, one for the point forecast and one for the quantiles, trained simultaneously with the MSE and the pinball loss. Finally, our model has 200,000 parameters, 3.8 tokens per parameter. Thanks for watching this video and have a wonderful day.